No one analyzes.
Yeah, no one.
Let me start also thanking the organizer for putting together an interesting workshop in such a wonderful location, and also giving me the opportunity to present my work. This is work done in collaboration with Stefano Giusto, who is in Padua, and a group of good and motivated students, Alessandro Bombini, Andrea Gagliani, and Emanuele Moscato. So let me start right away by saying what we calculate. So we focus on a superconformal field theory in two dimensions. And we calculate an observable, which is a correlator of 4 local operators. So with respect to the previous talk, these are local observables. And these operators are protected. So this means that their dimensions, this little h, are not dynamical, are completely determined by the R charges. And the dynamical information is hidden in this function, which is a function of conformal invariant cross-section. I mean, since this is a dynamical quantity, of course it depends on the theory, so I have to tell you what theory I'm looking at. And I'm considering a 4,4 superconformal field theory, which often is called the D1, D5 CFT, because it describes the low energy behavior of the open string stretched between D1 and D5 ring, type 2B theory. And it's holographic in the sense already pointed out in the original paper by Mandelstam that it's dual to type 2 string theory on a DS3 cross S3 times a 4-dimensional manifold, which could be either T4 or K3. It doesn't matter. Of course, if you want to calculate this observable, you can take, again, as mentioned in the previous talk, different approaches. You can do perturbation theory, you can try something just focusing on internal consistency of the CFT, like bootstrap. The approach I'll be discussing is using holography, so using the bar description to obtain this quantity. And this is most powerful when, again, as mentioned in the previous talk, the radius of anti-de Sitter is large. So it's large in comparison to the Newton constant. And that means on the CFT side that the central charge is big. And also when the radius of anti-de Sitter is large with respect to the string scale. And as usual, this translates into a CFT requirement saying that we are far from some free points. So this is a strongly interacting CFT. So from the CFT side, this quantity, as you see in the previous talk, would be hard to calculate. Okay, so after just advertising what the goal is, let me just say a couple of words of why the motivation. So one motivation for us to study this is to use this quantity to understand a bit more the microstate of extremal black holes. Right, so, and this explains this letter, big H and big L in this observable. These are not generic 4-dimensional 4-point correlators, but are 4-point correlators of an asymmetric type, where 2 operators are called heavy and 2 operators are called light. So let me characterize briefly what the difference between these 2 types of operators is. So the heavy operators are operators that still are protected, so they preserve some fraction of the supersymmetry. But their conformal dimension is large in the sense that it's proportional to the central charge. And as I was saying, the central charge is going to be large in this regime where holography is powerful. So this heavy operator can be thought as some particular state of an extremal black hole which has the same charges than the particular heavy operator that we are looking at. From the bulk point of view, since this dimension is of the order of 1 of the Newton constant, we expect that they back react, producing a non-trivial geometry that is only asymptotically at the S3 cross S3. But in the interior, it's different. And so we will be working with explicit classical solution, so metrics, B-field, the dilaton, that we would like to associate as the back reaction of these operators. The light states are just the standard fluctuation of the supergravity field. So dilaton, axion, metric. And their conformal dimension is of order 1, even if we take the largest one. Now, I can state just by using the standard dictionary, so using information from 20 years ago, what this correlator, what this dynamical quantity is from the point of view of the bulk description, is just a 2-point correlator of the supergravity field corresponding to the light operator we are focusing on, but not calculated in a DS3, but calculated in this background, which is only asymptotic. Once you calculate this 2-point correlator, then you take this 2-point correlator, you evaluate the boundary of the space. The boundary is still a DS3 cross S3, and that would be directly related to the 4-point correlator. Very good. So, if you have any question about the setup but anyway, just please feel free to stop me anytime. Okay, so the setup from the bulk point of view, as I said, is type 2B string theory. Now, let me just, for concreteness, focus on the case where the compact space, this M that I was discussing here, is just P4. And initially, we have an extra compact direction, I call it S1, different from this P4, because this is, if you wish, the spatial direction of the CFT. So the dual 1 plus 1 dimensional CFT will live in time and on this S1. Then this T4 will play very little role in what I'm saying, so you can almost forget it. And this is the space which is transverse to the D1 and D5. So it's the space where the solutions that correspond to the microstate black holes are not trivial. And the radial coordinate in this space is basically related to the radial coordinate of ADS3. So ADS3 will be T, Y, and something related to the radial coordinate of this arc. So if you start from the standard D1, D5 system, then this is the metric that you would write down. This extra bit corresponds to adding a third charge, which is the momentum. And you see that this metric depends on three harmonic functions, Z1, Z2, and this object there. And this is basically the simplest black hole that can be embedded in string theory, and maybe one of the motivations why we are focusing on this particular ADS-CFT duality, because it's the one that is where it's easier to make contact with black holes with large horizon area. And the contact with the black hole is, but you can think about this as just a 5-dimensional generalization of Reisel-Nostrum in 4 dimensions. Now with 3 charges instead of 1 charge. So in some sense, it's just a smart generalization of a very, very common type of black hole. The connection to the ADS3 regime is done by doing the usual decoupling limit, and then if you take the decoupling limit, this geometry becomes ADS3 cross S3 cross D. From the CFT point of view, so that would be the analog of ADS5 cross S5, if you wish, and this is the analog of n equal 4 superunit. So this is just a one slide about the CFT description. As I said, it's a 1 plus 1 dimensional conformal field theory, which is also supersymmetric. So it has an R-symmetry group, and being a 2-dimensional theory, this R-symmetry group becomes an affine symmetry. And this square is just because we have left-moving and right-moving component. And in some sense, it shares a lot of features similar to n equal 4. So that's good. It's just a bit more baroque. So while n equal 4 has 2 marginal couplings, if you want Gilliam Leach and the theta angle, this theory has 20. So you have 20 parameters that you can dial, and the theory is still super conformal. And exactly as in n equal 4, you have a special case when GM is equal 0, theta is generic, and that particular part of the conformal manifold is described by a free theory. This is true also in this case. You can dial down to particular value 4 of these 20 parameters, and then you have a 16-dimensional subspace which is described by a free CFT, and which is nothing else than a bunch of free bosons and a bunch of free fermions. And it's useful for us to keep in mind this free description because it's a language that you can use to describe explicitly some protected operator. So, as we often do in geometries when you describe protected operators as traces of elementary fields. So that's very much the same. The large central charge, where does this large central charge come from? Well, it comes from the fact that these free bosons and free fermions come in many different flavors, right? So you have lots of free bosons and lots of free fermions, and this is this index R that goes from 1 to n. So you have n copies of a free boson and free fermion theory. And all the non-trivial bit, which is also related to this four superconformal deformation that play the role of geometries, is the fact that this theory has to be symmetrized under the permutation group over this copy index, and that makes the theory a non-trivial orbifold, not just a free theory. Very good. Let me come back to the spectral flow later. So this is the CFT description, and so now I can just describe the two main players, the light operators and the heavy operators, which will enter in the definition of the 4-point correlator, which is the dynamical quantity that I would like to calculate. So for the light operator, we take the simplest possible. We will be working mainly with these two objects, these two examples of light operators. And these are probably the simplest thing you can write down. So using the language of the free CFT, one light operator, which is a chiral primary, actually an anti-chiral primary just for convention here, is just made out of one free fermion in the left moving sector and one free fermion in the right moving sector, right? So this object, as I mentioned, 1/2, 1/2. And this sum, right, you see it's a sum over all possible copies, ensures that this object is symmetric under permutation, right? Because you just sum over all possibilities. And this object, which is for many aspects even simpler, it's not an anti-chiral primary, but it's just a descendant of this, right? And you can almost see by directly by comparing the two equations. If you just act with one left moving charge, supercharge, you are transforming the fermion into the corresponding boson, and then you do the same thing on the right moving, and so that's kind of the first descendant with one step down, both on the left and both on the right. Now, what are the corresponding supergravity fields? Well, this has been, of course, discussed in the ADS3 cross S3 setup immediately after the paper by Mandelstam. There is a paper, I think, by Sedlin, Sundell, and other collaborators where they do the quadratic analysis of L2D supergravity around ADS3 cross S3. But in this setup, we need a bit more than that, because we want to study quadratic fluctuation not around ADS3, but around a generic background corresponding to the heavy operator. So disentangle the supergravity equation in that case requires a bit more energy. And one example you can see as the dual of this particular operator. The dual of this particular operator is on the supergravity side a fluctuation which is part in the axial field and part in the binomial field. So it's a coupled equation of a scalar and a two form, if you want. Now in ADS3 cross S3, you can write a specific ansatz of the tree form and the scalar, which both depend on a single scalar living only in ADS3, right? And this is what you would find in the paper by Sundell and collaborators. If you want to work the quadratic equation not around the vacuum, ADS3 cross S3, but around a generic state, then you would need to work with this coupled equation of a two form and a scalar. It's slightly easier, as yeah, people probably know, but we realized something later, to work with the descendant, because the descendant is a minimally coupled scalar in 6 dimensions, right? For not just a DS3 cross S3, but for a large class of geometry. So it basically has easier 6-dimensional equation that you have to work with. And another, okay, there are many things you see that are very, very parallel with N=4. Maybe one annoying feature that is different from N=4, so let me mention that, is that in N=4, if you fix the charges of a half BPS local operator, then basically you fix that, right? So you have just one multiplet of dimension 2, trace phi I, phi j. This is not the case in this theory, right? There is, for instance, here you have dimension 1/2, 1/2, but there is another operator, another chiral operator that has the same dimension, which is the twist field yeah. So this is something that is slightly different. Very good. So these are the light operators. So what is the role of the heavy operator? So we would like to write down operator was dimensioned as scales with C, is of order C. So one easy way of doing that, which is the main part, the main example that I will be focusing on, is to go to the Ramon sector of the conformal field theory, right? Because even the ground state in the Ramon sector have dimension which is fixed to be C over 24. So the dimension would scale with C. Right, so in order to go to the Ramon sector, there is, so this is this comment here, the standard way is to perform a spectral flow transformation, which is an isomorphism of the algebra and also of the Hilbert space of states in the Navier-Stokes sector, the states in the Ramon sector. And so you see from here, so this is the Ramon stress tensor, this is the Navier-Stokes stress tensor, that even if you start with the vacuum, the SL2C invariant vacuum, which is one state in the Navier-Stokes sector, right? So that would be 0 and 0. The stress tensor in the Ramon sector would be C over 24, as I mentioned. So that's already a heavy state. All the images of the anti-chiral primary operator, just in this convention of the spectral flow, will correspond to states in the Ramon sector with dimension C over 24. So there is a degeneracy of Ramon ground states that all have C over 24. So this map is depicted kind of, I mean, just the pictorial image would be enough for me. So this is the simplest example when you start from the Navier-Stokes vacuum, the SL2C invariant vacuum, and you end up with something that has dimension C over 24. So you can think about this state with dimension C over 24 as a collection of n copies, where C, the relation between C and n is that C is 6n. So you can think about it as a collection of n copies, and these n copies are these n copies, right? This is labeled by the index R. Where the fermions, instead of being in the Navier-Stokes vacuum, are in the Ramon vacuum, right? So that's the picture that I'm trying to convey here. You have a collection of n free CFTs, and each copy has one boson and two complex fermions. And the fermions in each copy are in the Ramon, are in one Ramon ground state. So you can see from this picture, if you think about the black hole interpretation, that this is a very special state. It's a very unnatural state. It's a state where all is made out of ingredients from the CFT point of view, and all the ingredients are all in the same state. Then you can try something more complicated, right? When you have n minus one copy in one state and one copy in a different state, and that would be, for instance, the spectral flow of the light CPO operator that we mentioned. Now, when are these states relevant? When do we have a nice gravity description of these states, right? So that's the question for us to be able to implement the program and calculate by using gravity. Well, the intuition is that we have a nice description if we have a lot of copies, a lot of objects that are the same, right? It's kind of the idea of coherent state type of states that we have in quantum mechanics, right? So if you have one single photon, even if it's very energetic, right, it's not described by a nice electromagnetic field. But if we have a lot of identical photons, then that object can be described by a classical electromagnetic wave, right? So the idea here is that in order to have a nice supergravity description, we need lots of these copies or strands that are the same, and lot means a number of them which is of the order of the central charge. It's some finite fraction of the central charge. And two main types of states we will be looking at is states that are like this one and this one, simple because you just have one type of object repeated many times, and states where you have more than one type of object, right? So this will be the more interesting, kind of slightly more typical. And this type of states, you see there is a sum. Again, the details are not important, but let me just stress that there is a sum. And so it is really a bit like a coherent state. And this state here, this type of state here, are determined by a continuous complex number, exactly like a coherent state is, this A and B, that basically weight the contribution of to the final state of term in the sum with different numbers of examples. Very good. So this is the CFT picture, and just please keep in mind the pictures because basically they should bring all the relevant information. Yeah, please.
These are stupid questions, but please. The Raman state vacuum has energy 0, right?
Yeah, or C over 24. I mean, depends how you.
Yeah, that's what I wanted to understand. In your conventions, the Raman state vacuum has what energy?
C over 24. So the dimension, I'm calling the dimension and I'm calling C over 24. So I'm just using convention where the NS vacuum has dimension 0.
Okay, thank you. So these various states are just the various zero mode states of the
Yes, exactly. So this is just, if I act with some zero mode, I transform this black thing in a blue thing, right? And this one would be acting not with a zero mode, right? So if we do the spectral flow of not anti-chiral primary operator, but a descendant, then we would get something which has energy above C over 20.
So these are all the microstates of the purely two charge.
Exactly. So these ones, and these ones are microstate of the two charge black hole. And I was trying to hide this, but okay, thanks to raise this point. So the advertising I did at the beginning had in mind the Schrödinger-Vafa black hole with 3 charges. But the actual calculation that we are able to do mostly focus on 2 charge. So the small black hole. The technology is general, but we'll see it just becomes more. Very good. So the main character will be a state like this, right? So again, it's a linear combination of Ramon ground state. So it's dimension C over 24. Is a microstate of the small 2-charge black hole that was just mentioned. And then I have to tell you what the gravitational description is. And there is a huge literature of this, starting around the 2000. Makur, Lunin, Maldacena, Maoz, a lot of papers writing down explicit solution that describe states like this one. And for instance, this one is described by this. And again, details are not important, but just I want to convey the idea that it's very explicit, right? So you can write down everything. So this is the ansatz of type 2B supergravity reduced to 6B. And then all these objects, like this is the 60 metric, this is the dilaton, this is the volume of the T4, the axion, right, the B field, the Ramon field, they are all written super explicitly. And you see they depend on 2 parameters, small a and small b, that are directly related to this big A and big B. So there is a 1-to-1 map, which is, the claim is very precise, is that, okay, this coherence type state is dual to this geometry, And again, in the CFT description, you have two parameters, but you have a normalization condition, right? The norm of your state is fixed, let's say 1. So this, with this convention, translates into something like a squared plus modulus over a squared plus modulus of b squared equal 1. So actually only one of these parameters is independent. And how do you see this in supergravity? Well, again, this was understood by the people I mentioned before. It's a regularity condition. So if you want the solution to be regular, then A and B to be regular in the center. So it's asymptotic, yes, but you go to the center, it becomes a curved geometry. Then the regularity condition imposes this. Right, and again, if you do the math precisely, this is exactly the normalization condition of the CFT. Okay, so what I want to say is that, okay, this is the setup. It's quite explicit, so one can just apply the standard technology of the CFT and calculate the correlators. So on the supergravity side, we should study the fluctuation around this geometry of the particular field which is dual to the light operator we're interested in. And this quadratic fluctuation, we need to impose two boundary conditions, right? It's a quadratic equation, so in principle it depends on two parameters. So we need to impose two boundary conditions, right? So one boundary condition is on the non-normalizable part of the solution, right, of your wave equation, right? And the non-normalizable part describes the position of the other light operator. So, for instance, if I want to put the other light operator to be at t equal y equals 0, right, then I would like to have a solution that behaves for its non-normalizable part around the boundary of S as a delta function centered in t equals 0 and y equals 0. So the first boundary condition is at the S infinity and tells me what the position of this other operator is. And the second boundary condition is at the center of S, where it's just a regularity condition. Right? So usually this type of wave equation is like, I mean, the type of that we can solve are just like a geometric, and so it will have a regular solution for in the center and a singular solution. So you'll take the regular solution, and that fixes for you uniquely this quantity, right? It fixes in particular the normalizable part of the solution. And that normalizable part is the correlator. Right? So this is what the CFT dictionary is. You need to solve a three-dimensional problem, even though at the end you're just interested on the two-dimensional part at the boundary. The condition at the center is what fixes this uniquely. Right, so you have just one.
Yeah. Sorry, I just wonder for this 6D metric, are you using the full Mandelstam Lewis metric, or you are taking the decoupling limit to?
Yeah, everything is in the decoupling limit here. Yeah. So you see, yes, very good. Yeah, sorry, that's a very good question. So this solution is for the asymptotically flat part, because if you are interested then in making connection with a flat, asymptotically flat black hole, then you need that. But for all my talk, I'm focusing on the decoupling limit because I'm doing an CFT calculation, so I'm dropping these ones. Yeah, so these ones are not there. So the problem, the actual solution is that without these ones.
Okay, so in previous slides, so you are doing perturbation for, the next one. So you are, I mean those pictures.
Oh, sorry.
Yes. So when you are doing the perturbation around 6D, so the first one should be the actual curve, the sextile metric, and the second one is the conical geometry. The second.
So okay, now this is not actual sextile. So this is I don't know, Mandelstam notes or Unimatura. I don't know exactly who was first. But basically this state is this solution with b equals 0.
Yeah.
Right? So, for instance, it still has this non-trivial bit, but some of these terms, right? So this goes to 0, right? This state here, yeah, as you said, okay, I was skipping this, but I'm happy to talk. Is locally at the S3, but it is an orbifold of the S3, so it's a conical defect. And it's related to the fact that you have these non-trivial periodicities. Very good. So this is the recipe. So basically what we're doing is looking at the Laplace. Yeah.
This correspondence between states and these geometries, there is some art in identifying that. But is there a more complete way? Since you mentioned coherent states, is there a way to show that this state would produce that geometry directly?
Yeah. So and let me say what we can do. One way of checking the dictionary is just repeating for this type of ADS3 what has been done by Shiraz and other people to calculate the three-point function, right? So basically using some, they did it for n equal 4 superunits, right? So using some quantity that we assume, that we know or we believe it's protected, and then check that protected quantity is the same, you get the same result by doing a free CFT calculation where you can use this language, or a strongly interacting CFT calculation, which is using the graphic language. And so Skanderis and collaborators started this, I don't know, around 10 years ago, and we pushed further this program to 3 charge states. And the program is to check 3-point correlators. So you can, instead of looking at 4-point, heavy, light, you do heavy, light, right? So that's not a dynamical quantity, it's supposed to be protected. And so basically you should be able to take this geometry, expand it around ADS3 cos S3, doing the S3 spherical harmonics analysis.